Hi gents, introduction to numerical methods of integration. Where you can get mathematical functions that you can integrate them using other methods, but they're a little bit tricky to integrate, and or where there simply isn't a method available, or you haven't got the function, you can use, it's possible to make use of approximation techniques called numerical integration to actually find a close approximation to a number of decimal places of the area underneath a particular function. So this is all about that practical use of integration, finding the area between functions or underneath a function, between the function and the x-axis. So what we're going to do is consider three different numerical methods, namely the trapezoidal rule, which we're going to cover this morning, and then when we come back, the first session back after half term, we'll be looking at the bisection rule and Simpson's rule. And one of the tasks in your assignment for this module involves you using one or two of those rules in comparison with a software method of finding the area under a curve. Okay, so trapezoidal rule. We've got a function. If we've got a function like the one shown there in the graph, y is a function of x, we could find the area between two limits, a and b, here and here, by integrating that function, finding the integral. If we divide that area between the limits up into n number of equal intervals of width d, and then connect the tops together, so at the top here, connect them together between the points of each interval, like that, we end up with straight lines, and we form trapeziums. Yeah. Now, the area of a trapezium can be found by half of the sum of the parallel sides. So if we take this first trapezium here, we'll add together the length of those two sides and half it, and multiply that by the width. Okay, so that would be one trapezium. Therefore, allowing for the fact that these lines at the top here are not an exact fit to the curve, we could say that the integral, the definite integral between a and b, is equal to, and then for each trapezium we take half of y1 plus y2, the two ordinates, so that's half of the parallel sides, and multiply it by d. We add all those up for all the trapeziums we've got in that particular, between the two limits, and we've got an approximation to the area of the curve. That can be further simplified to an approximation to half of y1 plus y2, y3, y4, y5, that's multiplying out the brackets, what to yn, plus half of yn plus 1. I.e., in summary, the trapezoidal rule is approximately the width of the interval times half of the first and the last ordinates, there and there, plus the sum of all the remaining ordinates. So you've got a formula there for the trapezoidal rule that you can apply. Okay, over here, I just popped it in up here. To find the width d for a given number of intervals, you take the lower limit from the higher limit and divide by the number of intervals, gives you the width d. So let's have a look at an example of using that. We're going to use we're using a function here that we know how to integrate anyway. Okay, so 5 minutes, probably less. Do part A and integrate that function. So going on from there, evaluating that integral. Area is equal to yep. 4 times 3 to the half minus 4 times 1 to the half. Yeah. .928 to 3 decimal places. Yeah, so that, gentlemen, should be the result you get by normal integration. Yeah? So what we're going to look at now is how close we can get to that by using numerical methods of a particular number of ordinates. So part B says use the trapezoidal rule with 4 intervals to evaluate the integral in part A corrected at 3 decimal places. So the first thing you need to do is find interval width D, and that is B minus A over the number of intervals, 3 minus 1 over 4 equals a half. So our interval width is a half. Then the best way to tackle this, we've got a function of y is equal to 2 over root x. We've got to find all these ordinates between 1 and in half steps between 1 and 3, isn't it? Yeah. So we want some kind of table really to do the value of 2 over root x for each of those ordinates. So a couple of quick minutes to fill that table in. We've got to calculate what the length of these, what y is at each ordinate. We've got to calculate it at 1, at half, at 2, 2.5, and 3. That gives us our ordinates. Yeah. So it's just 2 divided by x, 2 divided by the square root of the value of x at each ordinate. So what we got for these ordinates then, gents? When y is equal to, x is equal to 1, y is the function is equal to another good point here. How many decimal places do I want these ordinates to? Sure? You could do. That might not always be the appropriate thing to do. What Leibniz fractions you could do. But I would suggest we want 3 of our estimate. We should probably use ordinates to 4 decimal places here. Yeah? So 2 to 4 decimal places, the first one. When that's 1.5, what have we got? Yeah. 2, when that's 2. Two 2.5, 1.2649, and when that's 3, yeah. So by the trapezoidal rule, the area is half of the first and last ordinates, 2 plus 1.1547, plus all the other ordinates, 1.6329 plus 1.4142 plus 1.2649. Yeah? So we take half of the first and last plus all the other ones. And if you add all them up, I is approximately equal to what? Anyone got a final answer yet via this method? What we got then for the approximate answer to 3 decimal places? .944 square units. Yeah? And how does that compare with mathematical methods? Not very far out. Okay? So on the last page, not going to do that in class now, but between now and next time, can you have a go at doing that with 8 intervals, correct to 3 decimal places, and see how much closer that is? Okay, and then we're going to use a similar function with the other 2 methods as well, so you can kind of see all the way through which methods give the best answer and why. Okay, but that's pretty close. You think that's not far out, is it? And that's only using 4 intervals. If we used a piece of software that could take 100 intervals, you ain't going to be very far away from what the actual integral is. Okay? So we'll leave maths there today.